Hi everyone, in this video we are going to introduce the concept of energy of various forms and start talking about work and what work is with relationship to energy. So I'm going to be working through the slides here that are available on our course Blackboard page. I'll be using them to start our discussion of these things, and some of the problems that we're going to work are on these slides. So we start with this slide, which just sort of summarizes all of the different types of energy that we're going to be dealing with. Energy in general is a property of a physical system that stays the same within that system no matter what the interactions are within that system. Now, things can be outside of that system and act on that system, but if I've got some object, it has this energy. The energy may take various forms. We're going to do basically a bookkeeping process in order to keep track of all of those types of energy and how much total energy the system has. Energy is kind of an interesting concept in that we can't quite see it as looking the same all the time. Force is a push or a pull. Pressure, we'll see, is the result of particles slamming into the container that they're in. These are physical things that are always the same looking. Energy takes various forms. The total energy, however, we'll see stays constant because it's what we call conserved. So this picture here summarizes the various forms of energy that we have. We have kinetic energy, which we'll use a capital K to represent. That's energy of motion. We'll talk in another video about potential energy, either gravitational potential energy or spring potential energy. These are things that a system can have because they're off the ground or they're stretched. We have thermal energy, which we'll talk about later in the semester, but we'll mention in this chapter by way of friction. And then we have chemical and nuclear energy, which really are covered more in chemistry classes, but we'll touch on those things as well. You see that all of these things look very different. However, they're all types of energy that a system could have. It could be warm. I could be breaking molecules apart. I could be stretching something. I could be moving. Those are all different types of energy. This picture I am going to refer back to a lot. This is how I think of energy. We have some system that's a collection of objects or particles that we care about. We can put energy into the system to increase the energy of the system. We can take energy out of the system to decrease the energy of the system. This red rectangle just represents some stuff that we care about. The energy can go in via two different methods of transfer, which we'll talk about separately. The energy within can change varieties, which we'll talk about, and the energy can leave the system as well. So I'll be referencing this diagram a lot. This is one that I really like. This is the way that we keep stuff straight. We've got energy into our system, energy out of our system, and our job in this chapter is to keep track of this thing called energy and how much energy I have, what kind of energy I have in different varieties. That's really the name of the game. We're going to start by looking at energy going into the system. We have a collection of objects again, which is sort of this red rectangle. As we work problems, you'll see what I mean by the system, even though I've already thrown that term out a lot. And we're going to notice that work and heat are the things that can change the energy of my system. So I am going to change the mechanical energy of my system by working on it, or I could change the thermal energy, I suppose. But work is a mechanical energy change. That means I am moving something. I am pushing or pulling. I am acting on that system via forces, and I am doing what's called work on our system. That work will change the energy of my system. Now, what could that look like? Looking at some examples will help us see how the energy can change. So I could do work by pushing on this shot put sphere. And as I push on the shot put sphere, I know that I am moving it over a distance. And the difference in my system, it's going to look different. It's going to have kinetic energy now, because now it is moving when before it wasn't moving. So that means that I've changed one of the types of energy. I am now moving because I have pushed with a force. I've done work. Similarly, I could take a match and slide a match across a rough surface. That push is the work, and now I see that my system looks different. It's got thermal energy, right? Hot match, right? It looks different. I've got energy in my system. This little punk kid here, right? He's pulled back on this slingshot. So he's done work via that force of pulling. And we'll say that this system is a little bit scarier to look at than if he was just holding the slingshot. Why? Because there's energy stored in that system. There's elastic potential energy. So the system is different because we've done something to it. That something that we've done is called work. We'll go back to that equation. Let's talk about what work is, and in the next video we'll calculate it a few times. If I consider this system of a windsurfer, I've got this windsurfer that is just moving along the water. We'll assume that there's no friction between the board and the water. We know that the energy of this system is going to increase because here they are not moving at all. Their initial velocity is 0. And then at some later time they have a non-zero velocity. So I know that they are moving over here and they're not moving over here. And over this distance, something about their system has changed. We're going to say that that change is that they've got more energy. They are moving, they are not moving. That change is an increase in the energy of the system. Now, why did their energy change? Well, because this F represents the force of the wind pushing on them, right? That's what F represents. That wind is pushing on them. So as that force acts over a distance, right? I'm pushing here and I keep pushing over the entire distance that we move. As that force pushes on them, we know that their energy is going to increase because I'm pushing on them. The more I push them, the farther the distance is, we expect the more energy I'm pumping into my system. Similarly, the harder that I push, the more energy I'm putting into my system. So we expect that the formula that relates work and energy should depend on force and distance. And sure enough, it does. Here's our formula for work. The work that we do, W, is force times distance. It actually matters the angle at which I push. So there's this cosine term, because if I'm moving along this distance D, but I am pushing at an angle here as described in this picture, well, only this amount, this portion of my force that is parallel to my distance is actually going to speed me up. Right? We know from Newton's laws that this would just lift me off the surface a little bit if I'm moving in the X direction. So I only care about that horizontal component of my force, the force that is, we say, in line with my distance. That's why we have this cosine theta term. The units here would be in newtons and meters. So if we want to make a quick little note, the units here are in Newton meters, which we also call what's called a joule. So work is measured in joule, and we'll see all of our energy terms are in joules. In the next video, we are going to actually calculate work in a few simple instances, and then start talking about how we can calculate our specific forms of energy.